Day that is taking known series and manipulating. This is going to be a combination of 146 and 147 just because they go so well together. Would you start by writing the top four series, which you should definitely have down full memorized by now? If you don't, just get out. Say what form, so give me either expanded and the general or summation. I don't care either. Or both if you like. All right, how are you? We good? Okay. Now then, let's talk about how math is amazing, specifically calculus. Let's start by, what's this? That's not the word. Okay. So, check this out. Would you start by writing the f of x of sine of x, depending on how many terms could be approximated by the series, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Don't worry about the general, but continue, dot, dot, dot. Yeah? Now, if that's truly equal, then if I, by rules of math, if I do the same thing to both sides of the equation, equality should be maintained. And one of those operations I could do is differentiate. So would you differentiate both sides of that equation? I like it. I like it. How does 3 over 3 factorial clean up? 1 over 2 factorial. So that amounts to x squared over 2 factorial. 5's divide out, leaving you with x to the 4th over 4 factorial. Say we did the general term. The general term for sine is negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. The derivative on that then, negative 1 to the n, is coefficient, so it stays. But when you take the derivative on x to the 2n plus 1, what happens? By power rule, 2n plus 1 comes down, x to the 2n over 2n plus 1 factorial, but then a 2n plus 1 divides away, leaving you with 2n factorial. Isn't that cool? Now, that said, sometimes then, you're going to have choices. So say I have a question, find the Maclaurin series for 1 over 1 minus x squared. You could actually do that 3 different ways. One way is just to say, I don't recognize any relationship whatsoever, take the derivatives and find the derivatives and make the Taylor from scratch, right? From Maclaurin from scratch. You could do that. You could also say this is like the binomial series, 1 plus negative x to the negative second, and start doing your binomial work, putting negative x in to the binomial instead of a normal x. Or you could do the idea of what they're asking for, which is to say tie it to one of the 4 memorized series. Now, which one does that probably relate to? The 1 over 1 minus x. The question is, this is like 1 over 1 minus x, and then the temptation is that students say, okay, well, I could actually do that one of 2 different ways. This, you could either say 1 over 1 minus x squared is the square of the series, and we could do that. You sometimes square infinite series. You could say 1 plus x squared plus x cubed times, and so on, 1 plus x squared. You could do that. Or you could say, oh gosh, it's 1 reduced in power. And when we reduce by 1 in power, that usually means there's some kind of derivative in it, because 1 less power. You with me? Now that actually is the best way to go. The only thing you need to be wary of when you see a derivative relationship is sometimes it's not a perfect match. There might be an extra 2 in there, or an exponent, or a negative in there. So be careful. But the thought process, if you're going to try and match with the derivative, goes like this. Start with the known series. Which is that 1 over 1 minus x is 1 plus x squared plus dot, dot, dot. If you want to go back and find the general later, we can, but I'm going to leave that for now. Now, if I take the derivative of both sides, 1 minus x to the negative 1 on the left, and the derivative of the series on the right, then be careful. On the left, what is the derivative there? Negative 1 minus x to the negative 2 times an inside chain rule derivative of negative 1. Now that's actually perfect, because that means without any kind of playing around with it or having to make changes, I am getting what they asked about, 1 over 1 minus x squared. To finish up then, I just need to find the derivative of the right-hand side. What's the derivative of the right-hand side? 0 plus 1 plus 2x. What would the next one be? 3x squared, and so on. Now, if I had asked for the general term, I was very vague about this. I didn't say 3 terms or general term. But to write the general term, you could go one of 2 ways. It's nice to have options. One is just to analyze the pattern you see. In that case, for example, I can look at the terms there and say it looks like it's x to some power, and what's in front is what? 1 more, right? You with me? Okay. The other possibility is to take the derivative of the general term. Now, had I done that, then I would have said the general term is x to the n. What's the derivative of x to the n? N comes down, x to the n minus 1. Now, this disturbs students a little bit because it feels like I went about this 2 different ways and got 2 totally different results. Is that bad if those don't match? No, this term would actually be right there. It would be the one right before that. But either one could be used to find any term down the line. It is a general formula. Either could be used, even though they don't match 1 to 1. It's fine. You follow me? Okay. In choosing, maybe, if they had to do an interval of convergence test, one might be easier than the other. I don't know. All right, but that's the idea. You with me so far? Cool. Now let's talk integration. Just like through derivatives, we can actually find stuff through integration. Say you wrote the series for e to the x, which is 1 plus x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the n over n factorial. Now assuming continuity, which these are, I should be able to integrate both sides with respect to x. The antiderivative to the left is e to the x plus c technically, but just like in differential equations, we don't write a plus c on each side, we just write a c on one side, we're rolling them in together into one constant, right? So I'm going to write the constant on the right, but as opposed to how I normally do things, in a normal integral I'd write c at the end. This has no end, so we're going to write c first. C plus, and then the antiderivatives. What are the antiderivatives? X plus x to the first derivative is x squared over 2 times what was there, 1 factorial, right? And the next antiderivative is x cubed over 3 times the 2 factorial down there, plus, and so on. And the antiderivative of x to the n plus n to the n is x to the n plus 1 over n plus 1 times n factorial. Now, e to the x then is c plus x squared over 2 factorial plus x cubed over 3 factorial. Cha-cha-cha. To find the c, choose a wonderful x. What x? This should be true at any x in the interval of convergence. So, what is a good x to choose? Well, so let's say we use, think of good numbers, zeros and ones. 1 would stink because you'd have e equals c plus 1 plus 1. That would be yucky, yeah? Instead, choose x of 0, because then all that infiniteness goes away. You get e to the 0 equals c plus a bunch of zeros, and that implies then that c must be 1. That tells me that e to the x is 1 plus x plus, which we already knew. Now, on one level, you might say, that's stupid. Why would I take e and integrate it? Because it's going to be the same shape. I understand. It's kind of cool to prove that it is the case, but this is actually how you're going to get tons of other series. For example, we could get a series for natural log by using integration rather than taking derivatives and starting from scratch Maclaurin style, all right? So what is the relationship of log of 1 minus x to original 4? Which one does it relate to? I can imagine 2 answers, but only one check. Log of 1 minus x relates to 1 over 1 minus x. Somebody said e, which makes sense, but no, that's not it. Okay, so it relates to 1 over 1 minus x. So let's start, make that our starting point. 1 over 1 minus x is 1 plus x squared plus x cubed, cha-cha-cha. And then we say, all right, well, how will we get the left side to become like natural log? What is the relationship? Yeah, it's an antiderivative-y kind of one with maybe some playing around, but if I can integrate both sides, maybe everything will be great. Now, let's actually be careful though. What is the antiderivative of the left side? Is it log of 1 minus x? It is, by at least mental use of it, negative natural log of the absolute value of 1 minus x. And if I integrate the right side, it's c plus x squared over 2 plus x cubed over 3 plus x to the n over n, generally speaking. Okay? What's a good initial? You're going to choose your own initial. Choose an x for the initial condition. An x of 0. The natural log of 1 on the right equals c plus a bunch of zeros. For this one, the c is 0. Now, we're almost done, but we have one more thing. The negative of the natural log of 1 minus x is x plus x squared over 2 plus x cubed over 3. So the log of 1 minus x, which is what they asked about, is the opposite of all of those. You tracking? Okie dokie. So if I asked you to estimate the log of 2, how could you do it? How could you do it from first semester? How could you estimate the log of 2? Good review problem. A Calculus 1 student could estimate the log of 2 by saying it's the area from 1 to 2 under the 1 over x curve, yeah? And use trapezoids to do that, or Simpsons or what you want. That is the old school Calc 1 way. But a Calc 2 student might say the log of 2 is like the log of 1 minus 3 in absolute value, which is to say all of this with, so would you put 3? Yeah, it would be negative, would it be negative 3 or 3? This seems like this would be negative. That's not good. I have an error in my thinking. Right, so it should be positive. I mean, 2 is past. Oh, yeah, no. Log of 1 is 0. Log of 1 is positive. This should be positive. What's something breaking down? Do I have a mistake here in my work that I'm not seeing? Oh, that's what it is. You wouldn't do it that way because that's not applicable to the domain. It's not in the interval of convergence. Sorry, you would use an x of negative 1. That's how you do it. We'd have to study the interval of convergence for log here, but that's how you do it. And then this would be 1 plus 1. That would be it. Okay. Sorry about that. All right. Let's see. Do we have time for this bad boy? What time do we get out of here? Oh, cool. Yay. Okay. Now, this is definitely work smarter, not harder kind of thing. If I asked you to take the Maclaurin series for that, and you thought, well, sure, I guess I have to take the derivative and the second derivative and the third derivative, that would really stink because you got product rule like crazy, and they just would get worse and worse. Do you agree?
Yes.
All right. The beauty, that would be stupid. The beauty of this, though, is that this is like x squared times this series for e to the x. And you wouldn't really have to do all of that derivative work. You could just say, I need the series for x squared, or e to the x, excuse me, e to the x, and that is 1 plus x to the first over 1 factorial plus x squared over 2 factorial plus x to the n over n factorial, generally speaking. And then I would distribute the x squared to each term. So the series would be x squared plus x cubed over 1 factorial plus x to the fourth over 2 factorial. And what's a general term? X to the n plus 2 over n factorial. And wouldn't that be way better than taking all those derivatives? Yes. Let's change this to third degree, just because they threw out a total length. That's something I don't know. All right, so third degree of e to the x cosine of x. Now again, I have as an option taken the derivatives of e to the x cosine of x and then the second derivative. But again, I think you can expect that that would get some pretty gross product rule going on pretty fast, right? So let's think about this a little different way. I like to arrange this vertically, right small. So e to the x is 1 plus x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. And that's really all I would need to show, because anything more was going to get me something beyond third degree anyway. So I'm just going to go up to about third degree. Below that, I know it's weird to see a left justified multiplication problem. We're going to left justify a multiplication problem. And cosine is 1 minus x squared over 2 factorial. And I really wouldn't even need to write the x to the fourth over 4 factorial, because again, that would be too big. And it would be stuff beyond the third degree of the product. You with me? Now I'm going to multiply. I'm going to multiply 1 times each of these guys until I get to the third degree. When I do that, I get 1 plus x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. And I would keep getting factors, but that's all. Now I'm going to multiply the next term over in the cosine times each of these. X squared over 2 factorial times 1 is, or sorry, that's negative x squared over 2 factorial times 1. That is negative x squared over 2 factorial. Now it's up to me where I write this, but you want to write this where the like terms are lined up. So I'm going to write that here, negative x squared over 2 factorial. When I then multiply negative x squared over 2 factorial times x to the first over 1 factorial, that's negative x cubed over 2 factorial 1 factorial. And I would continue to get stuff, but that would be bigger power than I need for my final answer that they requested. If I then add, my final answer would be 1 plus x to the first over 1 factorial. What is the x squareds drop out, right? And then last but not least, I get x cubed over 3 factorial minus x cubed over 2 factorial. What's the common denominator there? That's x cubed over 6 minus x cubed over 2. What does that come out to be? Negative 2x to the third over 6, yeah? Or you could reduce that. Okay. But typically this would be a multiple choice question. You would, at that point, you would be done. You would find what you're looking for. See what I'm saying? Okay, cool. Is the function increasing or decreasing at x equals 0 here? Now again, you could do just say, well, geez, the first derivative is not too hard of that. I'm so smart with my calculus. I could do that, and you would be fine. But easier would be just to say f prime at 0 is what? In a Maclaurin series, isn't this f prime at 0 x to the first over 1 factorial? So what is f prime at 0? 1. It's 1, which is positive, and therefore f is increasing at x equals 0. You follow? All right, let's talk division. I know how you like long division. Well, we're going to long divide infinite series. That would be fun. So let's say I wanted tangent. the series for that. Again, I could say, I'm just going to start taking derivatives. And you could do that, again. But let's look at it maybe coming up with it another way. Tangent is sine over cosine. And sine series is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. And cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. Now, as tempting as it would be to say, I'll just cancel this, cancel this, cancel, that's not how the division of fractions works. We know that doesn't work. So instead, we're going to have to take 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, so on. Outside the box and inside the box is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. And here we go along dividing. How many times, now you look at the far left into the far left. So how many times does 1 go into x? X times, okay? Then I multiply. I get x minus x cubed over 2 factorial plus x to the 5th over 4 factorial. And so on. Then I get probably minus x to the 7th over 5 factorial. No, 6 factorial, right? Are you with me? Okay. In the long division algorithm, then, after I multiply, then what do I do with that? Subtract it. So I change every sign, draw the line, and I should be working rightward. X minus x is nothing. Negative x cubed over 3 factorial plus x cubed over 2 factorial. The common denominator, 3 factorial has 2 factorial in it, right? So you would need to multiply x cubed over 2 factorial by 3 over 3 to get the common denominator. So I get 3x cubed over 3 factorial minus 1x cubed over 3 factorial. That is 2x cubed over 3 factorial. Here, the common denominator is 5 factorial or 4 factorial? 5 factorial. I would need to multiply this by a factor of 5. So you'd have x to the 5th minus 5x to the 5th. That's negative 4x to the 5th over 5 factorial. Yeah, will you find the next one just to make sure you get the idea? So you're getting something like positive 6 x to the 7th over 7 factorial? Yes? Okay, now let's divide again. How many times does 1 go into 2x cubed over 3 factorial? 2x cubed over 3 factorial. And I was hoping I saw some kind of pattern there so we wouldn't have to keep doing this, but I'm not sure I know. It's obviously an odd pattern. Do you feel confident? I would be taking a stab at it. But at any rate, we could keep going. Now the good news is I've only seen this once on the AP test where you had to long divide. It's pretty tedious. Do you get the idea? Is that enough? That would be one of those you would come back to. You wouldn't take an L on it. Yeah, maybe it would have been easier just to. But gosh, then we talked about secret squares.
So is it just 144?
Oh, didn't I get 143 extra practice in yet? Really?
That's why I said you could not.
I assumed I I want 144 and 143 extra practice. Yeah. Have a great weekend.
Thank you. Sorry in advance.
What if I said 2144 or 2144? Oh. Stay out of trouble. Now you're going to lunch or first period, depending on your first period. Buenos dias.